Hello. Today and next maybe 2 nails we will talk about so-called abstract data types. And first I'll explain you why I choose this theme and this topic. Some days ago I had a discussion with some of my friends. They use Javascript on their work and they are funny and likes functional programming. And I asked them, so if you prefer JavaScript, JavaScript has lambdas on board, JavaScript has recursion, has everything, so why you do not program in a functional way, in a functional style on your favorite language? And I decided to hear something like, oh, it's not control of immutability, and something like that, yeah? But I received a valuable answer, and as for me, it looks reasonable. They answered, because JavaScript has not built-in effectively implemented functional data structures, data types. And I find out that, yep, of course, it's a real reason. That's why it's a modern hype to push into the initially imperative languages such like C++, Java, and maybe a lot of them push lambda inside of them. But anyway, it's not enough for making ability for using it in convenient and usable functional way, for functional style. Because for functional algorithms, for recursion, for immutability, we have to have a very effective and nice implemented, pure functional, I mean persistent and immutable data structures. And today I'll go into the little introduction of it, and later we will implement some of type of structures. Yes, of course, I know Clojure already has it on board, implemented very effective immutable maps, vectors, which are actually not real vectors, but maps with integer keys and very effective implemented, and sets and so on and so forth. But yeah, we will implement our own types just to show, just to see what's a good thing that Rich and his comment implemented and share it into the Clojure, and that's where we can use them. But let's talk first about existing languages and some mix of two different conceptions of operations and instructions. And actually that's that's the line where difference between imperative and declarative languages are aligned, and actually they are very mixed in usage in languages such as Java, C, raw C, C++, Python, and even JavaScript, and so on and so forth. So what do I mean? For example, we have a primitive types, integer values, let's see in a code, a equals by 1, b equals by 3, then we create a variable c, which result is the sum of a and b, and we create a variable d, it's a bit or operation of a and c, and then we can see the results, and nothing of these operations are really mutate or alter or change initial a and b values. It's nice fact really in assembler code. The sum operation, the bit or operation between two registers actually puts the results in the place of the first operand. But we are talking about our magic clean semantical world, and let's see that something in a magic world, in a magic RAM, random access memory, there are variables which either can be altered or not altered using some methods of these types. So integer types has a lot of methods, bitwise operations, arithmetic operations, and a lot of them. But most of them are actually not altered the initial arguments and operands of these methods. And it's quite a good thing, so it helps us to use these types, primitive types, in a functional way of programming, even in languages such as JavaScript and Python and so on and so forth. Also, we can create a string type, so-called. But for example, string replace function can work in both ways. Either mutate initial strings and do some replacing in place of its argument, or create a new one. Yes, of course, in Clojure it creates a new one, so we replace the characters A by characters B in initial string, but it keeps the initial string as it is. So we are moving into the more complex types instead of primitives such as numbers or bit masks. Yep, and it's good to have the same properties, immutability, and thus all the operations are immutable and do not alter or something put a garbage in initial values and so on and so forth. But yes, as you know, a lot of languages oriented in imperative paradigm has their complex types such as arrays, vectors, hash maps, maps, sets, with a lot of methods which actually mutate the actual value, so we cannot use them in our pure functional world and be happy. And also such a complex objects, such complex types, have to be persistent. What do I mean? For example, there are two sides of one medal: immutability and persistence. What do I mean under persistence? Let's imagine we have one list 1, 2, and second list based on previous one is count 0 to the initial list, and the results are first list 1, 2 and second list 0, 1, 2. Everything's fine. And what about persistence? The tail of B is actually A. So in memory, there would not be two different lists. There would be only two pointers. First pointer will set on some memory place where 0 value will placed, and the second pointer will actually place on the second element of list B. So the tail of list B is actually the list A, and that's why they two variables share their entries. And if we have not immutability, for example, let's imagine we can alter list A somehow, for example, change its last element from 2 up to 3. Yep. And then if we will do it, it also changes the last element of list B, because it's actually the same place in memory, it's actually the same the same data. Yep, and it's not a good thing while we have an ability to change one variable and some other variable may be changed or not. It's it's maybe leg shot, yeah, first. And so that's why persistent should be in a pair with immutability. And actually, the effectively implemented pure functional data structures should have three points: effectiveness, persistence, and immutability. And then let's go from the such a big theory to more practical thing. Why I called this namespaces ADT? It's not an algebraical data type like some Haskellers may think. It's the same abbreviation, but it's about abstract data types. So what do I mean? What means abstract? It means that we will have relations with the data types via its interface, and the actual implementation of these data types will not care us, and we can alter it later while we keep the interface and all the conventions on the interface the same. So that means the abstract data types. And I can show you some little example where you can find out this thing usable. Let's imagine that we have to collect the information from some stream, and stream can hold some numbers but in limited range, for example from 0 up to 10. Yeah, there are no any other numbers in the stream, but there can be any amount of ones, fives, any numbers of sevens, and so on. So it can be random order, but maybe number 4 will not present in this stream, but we have to collect, reduce this stream and collect the result, which numbers were actually in the stream. So how you will solve this task in a closure? Let's stop the video and imagine and think a little bit how you will solve this task. It's a very primitive and simple task. Oh. And for those who decide to continue, I'll share you some way. For example, let's imagine that we still not have so well implemented maps in a closure. Yeah, functional, persistent, immutable, effective, and shared, common parts, and so on and so forth. We can create our own type, and first of all we can start with interface. We will have 3 functions which allows us to work with this type. tNew, it's actually a constructor. Create a new item, a new entity of the object of type T, of our type T. It actually would be a primitive type number 0. We have to have a function of tadd. Actually it means that we have a type T, we have number n, and we have so-called set emulation. We have to add the number n into the type T. Actually it means that we will set the nth bit of number T in 1 into 1. Yeah, so that's why we will use bit OR and bit shift operation. And please keep in mind, please put your attention that here we will not alter or change or break somehow the initial value of T. We will return the new value of the same type with a set nth bit of it, but initial value will not change like we had it here before. All these operations on primitive types do not alter these values. And also we have a boolean predicate which can check of the nth position, actually the number n, is it exist in our so-called custom set as T. It actually implements as a bitwise AND of shifted 1 and the value of T, and check is it positive or not. How it works? Let's imagine we can create a new value of our so-called bit set. Then we set the first, third, and sixth bit of it into ones, and then we'll see the result. Yep, and it shows 0 bit is false, first bit is true, 3 is true, and 6 is true. All the others are false. And it works. It's actually implementation of our custom set with a lot of limitations. Yes, of course, we cannot add to this set some strings, maybe some negative values, some big values, more than 64, as I guess. Yeah, but if we fit all these limitations in our task, we can use it. And it's a pure functional data structure. It's persistent, and yes, it's immutable. We fit all the requirements we have for our implementation, the data types, so we're using it in our functional ways, in our functional algorithms. And now finally we can use it for solving our task. First of all, we have range from 0 to 10 with step 1. And actually we'll calculate which amount of divisions by 7 are exist in this list. we use our tinu as a starter for accumulator and simple reduce function, then we filter v by t@, for each value. And we see that we have all the possible values 0, 1, 2, 3, 4, 5 up to the 6. Yeah, but if we change the step to value of 2, we see only 0, 1, 2, 4, 6. If we change another way, 0, 2, 3, 6, only these values exist. So it's worked, and later, as I already said, we can alter the exact implementation of our custom abstract data type. We keep these all functions, we keep the conventions under it, but we can implement it not as a bit representation of long number, yeah, but some other way, and it will work the same, and all the usage, external usage of this our type created will work. So that's what I had to explain you in this nail. See you in next nail, where will we implement unidirectional linked list primitive. See you.